Bismillah ar-Rahman ar-Rahim. Today we will introduce the area problem, the problem that leads to what is so-called integral calculus. It is a very interesting problem. So the title is Area and Distances. We have the area problem, we have the distance problem. What is the relationship between them? How to find the exact area? How to find an approximation of the area? These are the main points will be discussed in this talk. Okay, I will start by listing the main points we have. We have the area problem, so we need to understand what is the meaning of the area problem. Then we will go through an approximation process, so we need to estimate areas, how to estimate areas basically using rectangles with different type of approximation. Then we will move to find the exact area under the curve, a given curve, okay? And finally we have the distance problem, and we will study the relationship between the first and the last one, the area problem and the distance problem. So let me start by explaining what is the meaning of the area problem. So what do we have here? If we consider this one as the y-axis here, and we have the x-axis, what we are interested in is the following. Here we have the x-axis, we have here the y-axis. If we specify a given function f of x here like this, for example, here we have y equal to f of x, assuming this function is always greater than or equal to 0. So if we specify two lines here, this is x equal to a, so this is a line at x equal to a, and this is at b, so we have the line x equal to b, so this is an interval now a, b. What is the area problem? The area problem is how to find the area under the curve above the x-axis between A and B. So actually what we are interested in is this. What is this area equal to? People are familiar of finding the areas if the sides are straight lines. For example, if you have rectangle, then the area is the width times the height, isn't it? If you have a triangle, then the area is 1/2 the base times the height. But if you have a curve, how to find the area under the curve? The idea is as follows. What we will do, first we will go through an approximation process. Then we will try to find a definition for the area. So we will start now how to estimate the area by using rectangles. And the idea is as follows. What we will do, we'll come to the interval AB. What we will do is just to partition this into some sub-intervals. Okay, so we will divide it into sub-intervals. How to do that? We'll take the distance b minus a and divide it by n. This will give me delta x, the length of each sub-interval if we do it uniform. Okay? Then what we will do, we'll try to draw some rectangles. Okay, we have the width here of the rectangle, but what is the height of the rectangle? Now it comes the idea of estimation. If we choose in each sub-interval the rectangle to be the altitude at the end, we will form a rectangle that's called right point approximation. If we choose the altitude to be the image at the first point in each sub-interval, we will call it left point approximation. If we choose it to be the midpoint height, then we call it midpoint approximation. So how to estimate areas under the curve, that will be our next point. Now what we will do in the first example, we will try to motivate how to find the exact area, but through an approximation process first. So what the statement of the question says, it says use rectangles to estimate the area under the parabola y equal to x squared from x equal to 0 to x equal to 1. Now what is the problem we have here? If you just see here the graph, this is the y-axis and this is the x-axis as usual. This is what we have. And we are trying to estimate the area under the curve y equal to x squared. Let us say this is the graph y equal to x squared. Okay, just a sketch of the graph to illustrate what is the problem here. This is y equal to, this is x equal to 1, this is x equal to 0. This is what is said by the question here, x equal to 0 to x equal to 1. Actually, what we are trying to find is the exact area here. But in this example, he said only estimate the area by using rectangles. Okay, in order to estimate, I need to control the number of rectangles. How many rectangles I need to form? He said you need to use 4 rectangles for the time being. Okay, how to form these rectangles? I will come to the interval and I will divide it into 4 sub-intervals. How to do that? Always delta x will be equal to b, the end of the interval, minus the beginning of the interval dividing by the number of approximating rectangle. If you apply it for this specific exercise, it will be 1 minus 0 divided by 4. And that is equal to 1 over 4. This will give me the length of each sub-interval. So the length of each sub-interval is equal to 1 over 4. Now you need to find the points. Okay, I find the points. This is 0. After adding 1 over 4, this is what you will get. This is 1 over 4. Adding another 1 over 4, this will be 1/2. Another 1 over 4, this will be 3 over 4. Okay, so we form the partition now. We have the first sub-interval, the second sub-interval, the third sub-interval, the fourth sub-interval. Now it comes to the height, the altitude. How to choose the altitude? Now it depends on the type of estimation you are doing. If he said you need to use the right endpoints, what does it mean here? It means if you come to the first sub-interval, you go and draw the height to be at the end. So this will give me the first rectangle because this is 1 dimension and this is the second dimension. So this is the approximating rectangle for the first sub-interval. Coming to the second one, this is the second sub-interval. He said choose the right point. So it means I need to go and draw the line here. That is the right point. So this will give me the second approximating rectangle. Then, similarly, I go to the third sub-interval. He said, you need to choose the right one. So this is the right one. So this will be called the third approximating rectangle. And similarly, for the last one, I go to the last point and I draw the rectangle. Now, if I need to estimate the area under the curve, what I will do, I will sum these areas of the rectangles. To have a notation, we will give the symbol Rn. That stands for what? The right approximation, meaning by choosing n sub-rectangles and choosing the height to be at the end of each sub-interval, the right point. So we give the notation Rn to indicate we are using right end point approximation. So what is, in our case, we are interested to find the area approximately. So it is approximately equal to what? R4, I'm using 4 rectangles with the right endpoint. So this will be equal to what? You know the area of the rectangle is the width times the height. So applying this, the width of this is 1 over 4. So it is 1 over 4 times the height here. The height is the value of the function at 1 over 4. Plus, second one, this is 1 over 4 and the height is the image at 1/2. Plus, the third one, 1 over 4 times the image at 3 over 4. The last one is 1 over 4 times the image at 1. So we can take 1 over 4 as a common factor. Then we multiply by f of 1 over 4 plus f of the second one, 1/2, plus f of 3 over 4 plus f of 1. Okay? So this is the width and this is the height of each sub-rectangle. Okay. Calculating this, you have 1 over 4 times. Now what is f of 1 over 4? We have the function f of x equal to x squared. So that is 1 over, this is 1 over 16 plus, this is 1 over 4. You secure each number. Then you get 9 over 16 plus f of 1 squared is equal to what? Is equal to 1. We need to simplify things and calculate. So what do we have here at the end? We get the area is approximately equal to R4, which is equal to, if you just look here, this is 1 over 4. Let us find the common denominator, that is 16. So what do we have here actually is this. I have over 16. So that is 1 plus 4 plus, because 16 divided by 4 is 4, multiplying by 1, that is 4. The next one, 16 divided by 16 is 1, so that's only plus 9. Next, I have 16 divided, this is 1 over 1, so I need to multiply by 16 up and down. This is what we have. So we are trying to now simplifying this expression, so to get the following, this is over 16 for sure, and that is now 1 plus 4 plus 9 plus 16. 9 plus 16 is 25 plus 5, that is equal to what? That's equal to 30. If you simplify things by dividing by 2 here, you get 2. If you divide by 2, this will be equal to 15. So the final answer in this case will be 15 over 32. That is what is so-called right endpoints approximation. In this example, we are using only 4 sub-rectangles. Okay. What other kind of approximation we can do? We choose here the altitude to be at the end of each sub-interval, and we called it right endpoints approximation. We may also use the left points to be the sample points, and we call it left point approximation. How to do that? With 4 rectangles also, on order just to compare ideas. We will do it in the next part. Okay. Okay, if we need to use now left point approximation, or we need to use 4 sub-rectangles or 4 rectangles to estimate this area under the curve by choosing the height to be at the beginning of each sub-interval, so we call it left endpoints approximation. How to do that? The same thing we have exactly done before. I need to divide the interval into 4 sub-intervals, so we will do the same. So the same step here is repeated. We have delta x equal to b minus a over n. In this case, it is 1 over 4. So I break this interval into sub-intervals. So what we have here is 1 over 4. I have here 1 over 2, and I have here 3 over 4. Okay. We have the width of each sub-interval. We need to choose the height of each sub-interval. According to what we specified here, left point approximation, it means this is the first sub-interval. You need to take the altitude to be the image at the beginning. But at the beginning here we have 0. And the image at 0 is 0. So the altitude itself is equal to what? 0. So our first rectangle is just the line segment here from 0 to 1 over 4. When you go to the second one is between 1 over 4 and 1/2. Choosing the first point to be the sample point, then we have this altitude here. So our rectangle will be like this. So this is what we have. That is our second approximating rectangle. The third one, I choose the altitude to be at the beginning here. So this is the height. So this will be our next approximating rectangle. The last one, we have 3 over 4 to 1. So I need to choose it at the beginning. So that is at the beginning here. And I need to draw the rectangle. So what will be the estimation of the area by using the left point approximation? I need to sum the areas of these approximating rectangles. So I need to get the area of the first one, which is clearly 0. I need to take the area of the second rectangle here, the third one here, the fourth one here, and sum them up to get an estimation of the area under the curve. And in this case, we will give a notation for this. We call it L4. It means I am choosing 4 rectangles and the height to be at the beginning of each sub-interval. The image at the left point of each sub-interval. In this case, I will get another approximation for the area, which is called, as we said, L4. So L stands for the left points. 4 stands for the number of approximating rectangles. In that case, the area will be the sum of these areas. So it will be what? The width as before is 1 over 4. There is no difference here. The first difference, here we choose the image to be at 1 over 4 and we called it right point approximation. Here we choose the image to be at the beginning, so it is f of 0. For the second subinterval, here we choose the image to be at 1/2, that is called the right point approximation. Here we choose it to be at what? At the beginning, so that is 1 over 4 plus the next one. I have this third subinterval. I will choose the image to be at the beginning, so it is f of 1/2 plus the last one is f of 3 over 4. 3 over 4 is the left point on the last subinterval. The last subinterval is 3 over 4 to 1. The left point of this subinterval is 3 over 4. So I choose the altitude to be the image at that point. If we calculate again this expression, I have 1 over 4 times, okay, f of 0 is 0. F of 1 over 4 is 1 over 16. Of course, you can write here 0 plus this, plus next one, 1/2 squared, that is 1/4, plus next one is 9/16. If you calculate this one after making the common denominator, you need to multiply by 4 here to make it 16. So this is 4 plus 1, that is 5. 5 plus 9, that is equal to 14/16, or you can write it as 7/8 by dividing by 2. Okay. Multiplying by 1/4, so the final answer will be what? It will be 7/32. That is the estimation by using what we call left point approximation. I need to do some, calculation here. 7/32, you will find that area is approximately equal to 7/32. This is approximately equal to what? This is in decimal notation will be written like, if you check this one, this is 0.21875. Now, let us take a note of the following. Now, we did 2 types of approximation. The first one here give us overestimate of the area. Why? Because whatever we get by R4 is more than the exact area. So we call it overestimate. So we are overestimating the area. By the second one, we are losing some portions of the graph here. So we are underestimating the area. So one estimation give us overestimate, and the other one give us underestimate. But one point of interest here that this exact area, it should be a number between what and what? Between the overestimate, which is 0.46875, and it should be greater than this number, 0.21875. So in conclusion now, we can conclude that our exact area supposed to be greater than this, less than this. Less than 0.46875 and greater than what? 0.2187 and etc. 5. The question now is how to get better approximation. How to get a better approximation, then how to reach the exact answer. We will observe this through an experiment. So what we will do now, instead of taking 4 rectangles, we will ask ourselves, what happened if we increase the number of rectangles? If we make them 8 rectangles, for instance, 16 rectangles, no, 100 rectangles, more than that, 1,000 rectangles. We'll see what will happen in this kind of approximation if we increase the number of rectangles. Okay, I will do it for 8 rectangles and for 1,000 rectangles, and we will observe what's going on for these numbers. Okay, that's our next point. Now let us see what happened if we increase the number of rectangles. So in this third part here, let us try to estimate the area by finding 8 subrectangles with the right endpoints and 8 subrectangles and left endpoints. And we need to see what's happening to this number, which is 0.46 something, and what's happening for this number, which is 0.21875. Okay, let us try to do first R8. In both of them, we need the width of the rectangle delta x, which is equal to, as we said, b minus a divided by n. In this case, we have, in the example here, we have 1 minus 0. The number of approximating rectangles here is equal to 8, so the width of each rectangle is 1/8. That is the length of each sub-interval. Don't forget, we are dividing the intervals to be uniform. I mean the same length for each sub-interval. Okay, good. How to find the points? When you go to the interval itself, this is 0, and this is 1, and we are making 8 sub-intervals. So the next one here will be 1/8. I'm adding 1 delta x here. Another one here will be 2/8, which is 1/4 if you like. The next one is 3/8, and the next one is 4/8 or 1/2, if you need to simplify things. Then this is what? This is 5/8. This is 6/8 or 3/4. Then we have 7/8, and finally we have it equal to 1, because once you add 1/8 again, you reach the last point. Now, if you calculate how many points we have, 1, 2, 3, 4, 5, 6, 7, 8, 9, But 9 points will give you 8 sub-intervals. If you count 1, 2, 3, 4, etc. up to this, you have 8 sub-intervals. Now, if you look for the graph, this is what we have. Again, this is y equal to x squared. This is y equal to x squared, assuming this is the point 1 and 1. And we are calculating the area up to 1 from here to here. This is the x-axis again, and this is the y-axis, and this is the function f of x equal to x squared. If we are making 8 rectangles, so this middle one will be 1 over 4. This is 1/2, okay, which is what? Which is 4 over 8. Then we need to make a partition like this: 1, 2, 3, 4. Okay, so this is 0, then 1 over 8, 2 over 8, 3 over 8, 4 over 8, etc. So this is 1 over 8. This is 2 over 8, that is 1 over 4 if you like. This is 3 over 8, okay? Then you do the same here. You have 1, 2, 3, and so this will be what? 5 over 8. Then we have 6 over 8, and then we have 7 over 8, and finally we have 1. Now how to choose the approximating rectangles? You do as follows. You go to the first sub-interval. If you need to calculate now R8, so this is R8. What is R8? It means you need to go and choose the right point to be your sample point. So this is the first rectangle, which is called approximating rectangle. The second one. You go to the second sub-interval. You choose the right point to be the altitude or the image of the right point. So that will give you the second rectangle like this. Go to the third one, do the same here. So this is what we have. Do the same. This is exactly what you have. Repeat the same thing here. You get another one. Repeat it again. You have a rectangle here. And again, for the one before the last one, you have this rectangle. For the last one, you have the altitude at the end. So that will give you the rectangles here. So we are forming an approximating rectangles or approximating rectangles. How many of them here? We have 8 of them. Calculating the sum of their areas will end up with an estimation of the exact area under the curve by using right endpoint approximation. So what is the answer here? Of course, we have here 1 over 8. Then I will not do the calculation. This is so simple. You just substitute 1 over 8. Then you need to substitute 1 over 4. And then at the end, you need to substitute f of 1. Okay? So you start with the point here to the right. You end up with the last point here, which is 1. If you calculate this, you'll have the answer is approximately is equal to, this is what I did, and I found the answer to be 0.398 what? 4375. Okay. What happened to the number here? You see R8 and R4. R4 is 0.46875. We know the area is less than this. But in the second approximation, we are getting smaller than this number. So we are getting closer to what? To the exact area. So we are expecting for increasing number of rectangles to get better approximation. Okay, let us repeat the experiment with the left points, and we will make 8 sub-rectangles. Okay, so that will be done like this. See, we need to keep these numbers so that we can observe what's happening at the end if you increase the number of rectangles. We are repeating the same experiment with L8. What is L8? It means you are finding an approximation of the area under the curve by using 8 sub-rectangles and choosing the left points to be the sample points, we call it. Okay, so this is the graph again. We have this, y equal to x squared. This is 1 and 1. This is 0, x-axis, y-axis. Here I am practicing drawing the approximating rectangles. And then adding the sum of the areas will give me an approximation of the area we are looking for. So what we will do again, we do the same story here. This is 1. So we divide it into 1/2. Then I divide this 1 here, 1. This is the same. I divide here into sub-intervals, 8 of them. Again, this is 1 over 8, 2 over 8, and so on, 3 over 8. This is 4 over 8. This is 5 over 8. This is 6 over 8. This is 7 over 8. And this is 1. how to draw the left point approximation and 8 subrectangles. Simply you go to the first interval, choose the left point. The left point here is 0, so the altitude is 0, so this is our first rectangle. In the second sub-interval, I choose the beginning of the interval, so that will give me another right rectangle and so on. You go to the last third one, this will be the approximate. The fourth one, I choose the left one here, so this is my rectangle. For the next one, I choose the left point, so that will be our rectangle, and you continue the same, so this will be the next one, and so on. This is what we have here, so that's the rectangle, and the last one is you choose the point here, so that will give you the rectangle. So summing now the areas of these rectangles will give me an estimation of the area by using what we call left endpoint approximation. Clearly here, L8, if you calculate, this will be just 1/8 times what? F of the left point, that is 0. Plus the next left point is in this sub-interval, which is 1/8. We need to stop at the left point of the last sub-interval, which is 7/8. What you need to do now, we take these numbers and substitute in the function y equal to what? Y equal to x squared, and then we add the areas. So what will be the area? What will be the calculation here? This is approximately equal to, if you calculate, this will be 0.27, okay, 34375. So what's happening to L4 here? We get it 0.21. This number is more than L4. So what happened? We are getting closer to the exact area. We are moving towards the area. So, interesting now, how to get the exact area. We need to think, what is the main point that makes a difference between the left point approximation and the right point approximation? The point that makes a difference here is the altitude, because the width is always the same. So the altitude at the beginning is not the same as the altitude at the end. So what should we do? If we can make these 2 points so close to each other, we are overcoming this difficulty. So what should we do? We need to increase the number of rectangles, keep increasing the number of rectangles. I will give you the calculation for choosing n equal to 1,000 rectangle. Look here. So delta x will be 1/1000. That is 0.001, close to 0. What happened at that case? If you calculate using a computer, for example, that will give you 1,000. L1000 is this is exactly equal to, or approximately to say equal to 0.3328335. Okay? If you calculate the approximation of areas by using 1,000 rectangle and right endpoints as altitudes, then you will get 0.33, okay, 38335. You can compare these two things. Okay, you can see up to the second digit, they are the same. So what's happening? As you increase the number of rectangles, the left point approximation is moving this way, and the right point approximation is moving this way. So one time, these two things will be what? Will be so close to each other. Now, if we can choose, let us say, if we can push the number of rectangles to be infinite. What does it mean? If you push number of rectangles to be infinite, it means delta x will be what? B minus a over n. If you are pushing n, the number of rectangles, to go to infinity, it means you are pushing this quantity to go to what? To 0. Meaning, the beginning of the interval or the end of the interval, we have very small distance, meaning the altitude at the beginning, the altitude at the end will be almost the same. If you push this n to go to infinity, that will lead us to the exact area under the curve. So the next point is how to find the exact area under the curve. We will do it for this specific exercise, and we will see what is the exact area under the curve y equal to x squared from 0 to 1. That will be next point. Okay, let us move a little bit further to reach the idea of, or the definition of, exact area. So one last step we need to do before we go to the exact definition, or the exact area of under the curve. Let us find Rn, meaning I am now letting the number of rectangles to be n, and I will choose the right endpoints to approximate the height. Okay, what is Rn? What should I do? I need to go to the interval I have, which is called AB. I will call this one the first point x0, this is A, and the last point I call it xn, that is equal to B. What I will do, I will partition this interval. I will divide it into n equal sub-intervals. So how to do that? I will go to delta x, that is equal to b minus a divided by how much? N, right? And what are the xi's? The sample points here. I need to choose the right points. Or let us see how to choose the right points. How to get x1? x1 is simply equal to x0 plus what? Which is a, in this case x0 is a, so let us replace it by a. It is the beginning of the interval plus one distance here. This is equal to what? Delta x, so it is 1 delta x. If I need to go to the second point here, x2, I need to move twice the distance. So this is a plus 2 delta x, and so on. So in general, what is the ith sample point? It is a plus I times delta x. You see, the first point is a plus 1 delta x. The second point is a plus 2 delta x. The third point will be a plus 3 delta x. The ith point is a plus I delta x. So using these items we have here, that will help us to find the Rn for our previous example, that is y equal to x squared from 0 to 1. Let's go back to our example now. We have the interval between 0 and 1. This is what we have, 0 and 1, okay? We are trying to form n sub-intervals, so this will be what? This is 1 over n, this is 2 over n, and you move up to the one before the last one is n minus 1 over n. The last one is n over n. You keep adding 1 over n, and etc. until you reach the last point. We have now n sub-intervals. Okay, going to the graph again, this is what we had before, x-axis, y-axis, we have y equal to x squared. Here, this is 1. So we divide it into sub-rectangles like this, and we have n of them. I'm choosing the height to be at the end point, so what do we have? I will have the following. This will be the area, the area is approximately equal to Rn, which is equal to. Now, the width is 1 over n. The width of each sub-interval is 1 over n. What about the height of the rectangles? For the first one, I chose it to be the image at the last point. So that is f of 1 over n, something like this. For the second point, for the second sub-interval, I choose the right point. So it is f of 2 over n, etc. until you reach the last one, the last sub-interval. That is f of, if you like, you can write it as f of n over n. That is f of 1, n over n. Now, instead of dealing with such kind of notation, we can rewrite this one as a summation notation. Meaning, okay, let us try to keep this in front of us so that we can compare with the exact area. But we can ignore these things. We don't need them now. So we are done with the estimation. We are trying to reach now the exact area of the region under the curve. Okay. I can write Rn like this. Look, Rn, I can write it this way. It is summation. I have an index I is running from 1 to n. Then I have f of the xi's multiplied by delta x. This is the width of the rectangle. And this is the image at each right endpoint of each sub-interval. Okay, so for this our specific exercise, this is what we have. We have I equal to 1 up to n. What are the xi's? We said the xi's a plus I delta x. In our case, a is 0. So this is 0. I delta x, our delta x is b minus a over n. That's 1 minus 0 over n. That's 1 over n. So our delta x here will be, in our specific exercise, 1 over n. and the xi's will be I times 1 over n, that is I over n. Taking these 2 points and substitute in the formula we have here, that will give you what? The function, don't forget, f of x is what? X squared. So what are the f of xi's? It means f of I over n. F of I over n multiplied by delta x, that is 1 over n. Okay, fine. Look here. Our summation depends on I. So 1 over n has nothing to do with I. So I can take it outside the summation. This is 1 over n. Summation of I equal to 1 up to n. What is f of I over n? Substituting here, you get what? You get I squared over how much? Over n squared. I'm taking the number and square it. Good. Now, again, n squared has nothing to do with I. I can take it out. So this is 1 over n cubed multiplied by summation of I equal to 1 up to n of I squared. Now, it comes the beauty of these formulas we have here. That's why always, if we need to succeed in evaluating the exact area for some specific functions, these formulas will be of great help. Okay? I will use now the third one of them. So I will replace the summation of I squared. What is summation of I squared? This is 1 over n cubed, and I replace this now by the expression there, that is n plus 1, what? 2n plus 1 divided by how much? Divided by 6. Okay? That gives me the area or estimation of the area by using n rectangles. We are not specifying in here. If you choose n to be 4, you will go back exactly to R4. If you choose n to be 8, you get R8 and so on. Now, what's our target here? We said we are trying to minimize the distance between the left point and the right point. If we can make it so close, meaning if we can make delta x approaching 0, then we are minimizing the errors in the calculating the area. So what we will do here, we will study now what will happen if we push the number of rectangles to be infinite. So we are going through a limit process now. So we are taking the limit of Rn, meaning we are pushing the number of rectangles to be infinite. So the left point, the right one will be the same. So, or almost the same. Okay, so what will happen now if we just take the limit of Rn? Look here. What is the limit as n goes to infinity of Rn? What is the answer? It will be the limit as n goes to infinity of that expression we found, which is something like n plus 1 to n plus 1 and divided by what? 6n cubed. And from your previous studies, you know that this is a polynomial of degree 3 and this is polynomial of degree 3, and you are taking the limit as n goes to infinity. So it is enough to take the leading term over the leading coefficient over the leading coefficient. That is 2n times n times n. That's 2n cubed over 6n cubed. So the final answer will be 2 over 6, which is what? 1 over 3. Interesting now, what we did here is the exact area. Why? We are pushing n goes to infinity. It means the left points and the right point will be the same. So the altitude at the beginning or at the end will not make a difference. So we overcome the problem that makes a difference in the estimation. So what is now the exact area under the curve? The answer will be 1 over 3. Let us look for our estimation if it makes sense or not. What is 1 over 3? 1 over 3, if you just divide 1 over 3, that is what? That is a 3 by 3, this will be 9. Again, you have 1, 10. So what you get at the end is 0.3, 3, 3, etc. You remember our calculation did before? We reach R1000, and let me remind you of these numbers. I have them here. We get, if you remember, this is L1000, for example. We get it to be approximately equal to 0.3328335. We get R1000, okay, to be approximately equal to 0.3338335. You see, we have here a number which is close to the exact. And here we have a number which is close to exact. So yes, by increasing number of rectangles, we are getting better approximation. But in conclusion now, if we need to hit the exact area, what should we do? We need to push in to go to what? To infinity. So that is exactly the definition of the exact area under the curve. We will write it now as a summary. What is the meaning of the area under the curve? Now let us come to answer the question we started with this talk. What is the meaning of the area under the curve? What is the exact area under the curve? This is the problem we are facing. We need to find the area under the curve. Now by the discussion we made, by the approximation process we made, by the limit test step we did, it says now what you need to do, you go to the interval you have A to B, and you break it into n sub-intervals. So you have x0, x1, x2, xi minus 1, xi, xn minus 1. The last one will be xn. You have n sub-intervals. So you draw the rectangles now. Now it doesn't matter now if you push in to go to infinity, these points will be so close of each other. So it doesn't make a difference if you choose the sample point to be the first point, or you choose the sample point to be the right point, or you choose it to be the middle point, or any point in between. So the definition says the area A of the region which is here, this is the region A or the area A, and this is the region S. So the area A of the region S that lies under the graph of the continuous function f of x. Of course here we are assuming that this is always greater than or equal to 0, above the x-axis, is defined by. Now let us look for the definition. It says you can find the approximation by right endpoints and you push and go to infinity. You get an exact area. Or you can take the limit of the left endpoint approximation by taking endpoints. That will give you the same answer. Or it says in general you can take any point xi star that is between xi minus 1 and xi. What does it mean? You go to the first sub-interval. You can choose the point or the height to be at the beginning, the height at the end, the height at any point in between A and x1, x0 and x1. It will not make a difference once you push in to go to infinity. It doesn't make a difference in the final answer. You take the left point, you take the right point, you take any point in between as a sample point. The final answer, as you push in to go to infinity, you get the same number, a unique number. And that unique number is the area under the curve. So this is what is the summary of what we did. And now we need to focus in these items that are very important in the definition. So I need to understand what is delta x, that is the width of each subrectangle. These are called the sample points. Now this will give you the right endpoints. This is the right endpoints. If you like the left endpoints, what you need to do, you need to take xi minus 1. So here you have I minus 1. Okay? So practically we either use the right endpoint approximation or the left endpoint approximation by n rectangles. Then we push in to go to infinity. We will reach the exact area. We did it in example number 1. The area or the exact area under the curve y equal to x squared. By pushing Rn to go to infinity, we get the exact area, which is 1/3. So now we reached the idea of, or the definition of what we call exact area. We are done with the area problem now. What do we need to do next here? I will show you now a third type of approximation. It is called mid-point approximation. So what I will do in the next paragraph, I will summarize for you what we did. So I will solve an example about left point approximation. I will solve an example about the right endpoint approximation. And we will solve an example about mid-point approximation to summarize what we did. Okay? And then we will move to what we call distance problem. Okay. Let us see how to approximate area under the curve by using different approximating rectangles. Let us come to the first exercise here. The exercise says, estimate the area under the graph of f of x sine x over x from x equal to 0 to x equal to pi by using 4 rectangles and right endpoints. Take a note of this. The first one. We consider the area under the graph because you can see the function here, f of x sine x over this specific interval from 0 to pi. This is non-negative, so it is greater than or equal to 0. Okay, this is one thing. The second one, in these type of questions, always there's supposed to be a function, there's supposed to be an interval given, and also the number of rectangles will be specified. You remember, we had the left point approximation, we have the right point approximation, and we said we will talk about midpoint approximation. Here, he's asking to find or to approximate the area by using right end points as sample points. How to do this? Simply what you need to do at the beginning is to find delta x. You remember what is delta x? Delta x is b minus a over n. A is the beginning of the interval, b is the end of the interval, and n is the number of rectangles. Okay, let us calculate delta x. What is delta x? Delta x here is equal to b minus a, so it is pi minus 0 divided by the number of rectangles is equal to 4. So that is equal to pi over 4. Okay, interesting. Now let's come to the interval given and try to partition it. So what do we have? We have from 0 to pi. So this is 0 to pi. This is what we have. This is 0 and this is pi. Our delta x is equal to pi over 4. And we need 4 rectangles. So this is one, let us say. This is second one. This is a third one. So what are these numbers then? 0 is the beginning of the interval. Adding delta x, you have the second point. So it is pi over 4. Adding another delta x pi over 4, this will be pi over 2. Adding again pi over 4, this will be 3 pi over 4. So you can see now we have 1, 2, 3, 4 intervals or sub-intervals. Now what is the altitude? The altitude will be taken as the right endpoints, the image at the right endpoints. So how to find out the area or how to approximate the area? The area will be approximately equal to, as we said, it is the summation I equal to 1 up to 4 of f of x is delta x. So simply will be equal to what? What is our delta x? Our delta x is pi over 4. So I will say pi over 4 is common factor. Then what is the value now? F of what? In the first sub-interval, we take the right point. So it is pi over 4. So it is f of pi over 4. Okay, plus the second sub-interval now. This is the second sub-interval. I will take the image at the end point. The image at the end point, that is f of pi over 2. Okay, plus next one, the third sub-interval. I'll come to the last point here, which is 3 pi over 4. So that is f of 3 pi over 4. And finally, in the last sub-interval, I will take the endpoint, which is pi. So it is f of pi. So you can see now, pi over 4 times this will give you the area of the first rectangle. Pi over 4 times this will give you the area of the second rectangle. Pi over 4 times this will give you the area of the third one, and so on. Pi over 4 times the last one will give me the area of the fourth rectangle. Now, calculating this will give us an estimate of the area as required in the question. So it is pi over 4 times. Now let us do the calculation part. What is f of pi over 4? This is the function given here. So I need to substitute pi over 4. What is that? It will be sine pi over 4, all of this divided by pi over 4. It is sine x over x. Plus, similarly here, it will be sine of pi over 2 divided by, this one is divided by pi over 2. The next one, 3 pi over 4. So it is sine of 3 pi over 4 divided by 3 pi over 4. And finally, we have sine of pi divided by pi. Okay, this is what we have. Now let us find the numerical values of this. Pi over 4 times. Now what is sine pi over 4? Sine pi over 4 is nothing but radical 2 over 2. This is 1 over pi over 4. I will write it as 4 over pi times the value of this, that is radical 2 over 2. That's the first item here. the second one. I will have sine pi over 2. You know, sine 90 degrees, sine pi over 2 radian. That's equal to 1. So this is nothing but 2 over pi, if you like, times 1. Okay? Times 1. Next one. Plus. Now, sine 3 pi over 4. How to calculate sine 3 pi over 4? You know, 3 pi over 4 is in the second quadrant. And the reference angle here is pi over 4. Okay. This is 3 pi over 4. So sine of 3 pi over 4 is the same as sine pi over 4 because in the second quadrant the sine function is positive. So what is the answer then? It will be, this will be 4 over 3 pi times sine 3 pi over 4, which is sine pi over 4, that is radical 2 over 2. Plus the last one, sine pi. Sine pi is 0. So the last item will be what? Will be 0. So that is the evaluation part of the last term. Now, let us simplify more. This is pi over 4. You can now see I can divide by 2. This is dividing by 2 will be equal to 1. Dividing this one by 2, this will be 2. So that will be 2 radical 2 over pi. 2 radical 2 over pi. Okay, the second one is already in simplest form. So it is 2 over pi plus. The next one is, again, if we divide by 2, this will be 1. Dividing by 2, this will be 2. So it is 2 radical 2 over 3 pi. Okay, fine. You can do this if you like. You can find the common denominator first. So that is pi over 4. I will find the common denominator, which is the LCD here is 3 pi. So I multiply here by 3. I will multiply here also by 3. This will be 6 radical 2. Plus the same thing I did here, I multiply by 3, I will multiply by 3 here, that will be equal to what? That will be equal to 6, plus I did nothing here, I just multiplied by 1, so I will multiply here by 1, that is 2 radical of 2. Now this is equal to, simplifying more, 6 radical 2 plus 2 radical 2, that is 8 radical 2, so this is pi over 4 times 8 radical 2, okay, plus 6 divided by 3 pi. Now, if you like, you can cancel the pi here with the pi here. Just they are the same, so I can cancel them out. And also, you can divide by 2 and divide by 2 these two terms. You can take the 2 common factor and simplify. So this will be just 4 radical 2 plus 3. Because if you take 2 as a common factor, okay, and deleted with the 4 here, this will be 2. 2 times 3 will be equal to 6. So this is the area or an estimation of the area by using 4 rectangles, right endpoints of the area under the graph of f of x sine x over x. Now, we need to take another example and see how to apply this, the same idea with left endpoint approximation. So we'll take now another example to show you how to evaluate or to find an estimate of the area by using left point as a sample point. So that will be our next example, and our next example says this. Example. The example here says, use 3 rectangles. Use 3 rectangles. So I'm using 3 rectangles, and I'm taking the left point up. So the sample points here for this exercise will be the left points. To estimate, again, we are talking about estimation. So to estimate what? The area under the graph, the area under the graph of, look here, it is f of x equal to x plus cosine squared of x from x equal to 0 to x equal to pi. Interesting. So we are using the left point as a point of approximation. The number of rectangles are specified. He said 3 rectangles. So this is our n in the formula. And we are given a function that is non-negative over this period. And that's why maybe someone asked, why we have a sec word here? X plus cosine x. This sec word will ensure that this function is non-negative between 0 and pi. You know, the cosine function is positive between 0 and pi over 2. But it is negative from pi over 2 to pi. By putting this sec word, this is always non-negative. And also this is non-negative. So the area under the curve will be estimated now by using 3 rectangles. And we can talk about the curve, which is non-negative, and we can talk about the area under the curve by this procedure. Okay, how to find the answer? Again, we will start finding delta x. We will start finding delta x. What is delta x by formula? It is b minus a divided by n. Again, I said a stands for the starting point, b is the end of the interval, and n is the number of approximating rectangles. Fine. So in our case here, a is equal to 0, b equal to pi, and n is equal to 3. So it is just pi minus 0 divided by 3. That is equal to pi over 3. Now we'll come to the interval. The interval we have starting with 0. I'm adding 1 delta x, so it will be what? It will be pi over 3. Another one, pi over 3, this will be 2 pi over 3. Another pi over 3, we will reach the end, that is equal to what? That's equal to pi. So you start with the beginning, adding delta x, you get the second point, adding another delta x, you get the third point, adding and so on until you reach the end of the interval. So you can see now we have 1, 2, 3 subrectangles with equal width. But what about the altitude of each rectangle? In this exercise, he said you need to choose what? You need to choose the left points. So this will be in the point will be taken in the first subrectangle. In the second subrectangle, I will take the left one. In the third one, also I will take the left end point. So what will be the area? The area is approximately equal to what? What is delta x? Pi over 3. So that is pi over 3 times. This is the width of each subrectangle. What about the altitudes? It will be f of 0 plus f of pi over 3. That is the second sample point plus. Now, the third sample point will be 2 pi over 3. So it is f of 2 pi over 3. Okay? This is the formula that approximates the area by using 3 subrectangles and using what? The left point approximation. Okay, fine. This is equal to what now? Substituting will give us the answer. This is pi over 3 times. What is f of 0? This is the function. If we substitute 0, this will be 0. Cosine 0 will be 1. So 1 sec word will be 1. So this is simply equal to 1 plus. What about f of pi over 3? Okay, this is pi over 3. So this is pi over 3. Plus, now, cosine sec word pi over 3. Cosine pi over 3. Cosine 60 degrees. That's equal to 1/2. When you square it, you have what? You have 1 over 4. This is 1 over 4. Plus, coming to this is the second evaluation. Now, this third one. 2 pi over 3. Of course, this will give us 2 pi over 3. Okay? Plus, what about cosine squared 2 pi over 3? Again, 2 pi over 3 is in the second quadrant. Look, it is in the second quadrant, 2 pi over 3. Terminates in the second quadrant. This is 2 pi over 3. The reference angle is pi over 3. But cosine in the second quadrant is negative. So the value of cosine 2 pi over 3 is equal to minus cosine pi over 3, which is minus 1/2. But here, does it make a difference? Why? Because we have squared. We have squared here. So simply, it is minus 1/2 squared. That is again 1 over 4. So that is interesting. Now, how to simplify this expression? We just add similar terms. So I have 1/4 plus 1/4, that is equal to 1/2, plus 1, that is 3/2. So I will write this one as pi over 3 times, this is 3/2 plus. What about the pi over 3 plus 2 pi over 3? That is 3 pi over 3, which is actually equal to pi. So this is the answer. You can also write it in another form if you like. You can multiply by pi over 3. So this will be pi. You can see now the 3 will cancel with the 3. So it is pi over 2 plus, if you multiply here, that will give you pi squared over what? Over 3. Now, you remember we discussed now the left point approximation and the right point approximation with different examples. And these are two samples of right point approximation and left point approximation with different number of approximating rectangles. The next point will be, what is midpoint approximation? Now, what is midpoint approximation? Simply, midpoint approximation is given by this formula. Mn equal to I equal to 1 to n, f of xi bar delta x. What is the sample point chosen here? It is the midpoint of each subinterval. You go to each subinterval, don't choose the left point, do not choose the right point, take the point in between, the middle point. So we call it midpoint approximation. If we go back to the starting point we did today, just to show you what is the meaning of midpoint approximation, if you go to y equal to x squared again, this is the example we did from 0 to 1, right? This is the x-axis, the y-axis. We did left point approximation, we did right point approximation. Now what does it mean, midpoint approximation? If we decide to make 4 rectangles again, so this is what we have. We said this is 1 over 4, etc. if you remember. This is 1 over 4, 1 over 4, that is 1/2. This is a 3 over 4. At that example, we did left point approximation by choosing the sample points to be always the left points. We did right point approximation by choosing the right points to be the sample points. There is another type of approximation called midpoint approximation. How to do that? How to find the midpoint approximation? You go to the first subinterval and choose the middle point here to be the sample point. How to find the middle point? You need to add them, divide by 2. So 1 over 4 plus 0, that is 1 over 4, divide by 2, that this will be 1 over 8. So our sample point number 1, x1 bar, will be what? 1 over 8. So what should we do? We go here and draw the altitude of the rectangle. So this will be our approximating rectangle. Look here. We choose the height to be the height of the middle point. Okay, when you go to the second one, same thing. You go to the middle point here, draw the height. So this is your approximating rectangle using the midpoints. If you need to find exactly what is this point will be called x2 bar, the second sample point as a midpoint. It will be adding these two numbers and divide by 2. So you will have 2 over 4 plus 1 over 4, that 3 over 4, divide by 2, that is 3 over 8. Similarly, you do for the third one. You go to the middle point here, sketch the altitude, and then draw the rectangle. Okay? That's the rectangle we have here. So what is that point exactly here? What is x3 bar? You are adding these two numbers. 1, okay, you are adding 3 over 4 plus 1 over 2 and divide by 2. This is 2 over 4 plus 3 over 4. That is 5 over 4. Dividing by 2, that is 5 over 8. Next one. The next one here, you just go to the middle point, go to the altitude, graph the rectangle. So you see different type of approximation we have here. The fourth sample point, the midpoint in the last subinterval, you need to add 1, which is 4 over 4, plus 3 over 4, that is 7 over 4, dividing by 2, that is 7 over 8. This is one way to do it. Another way to do it, you have x1 is 1 over 8, you have delta x is 1/4, so you start adding 1/4, 1/4, 1/4, until you reach the last subinterval to get the sample points. Now, if you need to calculate the area by using midpoint approximation and 4 rectangles, that is called M4. What is the answer here? Delta x is the same, 1 over 4, but you need to evaluate the image at not the beginning, not the end, the middle one. The same thing for the second one. It is f of the middle point, 3 over 8, plus f of 5 over 8, plus what? F of 7 over 8, and that will give you another type of approximation called midpoint approximation. Don't forget, here we have the graph, f of x equal to what? Equal to x squared. It remains just to substitute here, adding numbers multiplied by 1 over 4. Now I will show you another concrete example how to calculate the estimation of the area by using midpoints and different functions. This is the basic example we did just to illustrate how to, or to motivate how to find the exact area by the approximation process. Now I will give you another example how to calculate the midpoint approximation of the area by using a certain number of rectangles. Okay? So that will be our last exercise for estimation of areas. Then we move to the second point, which is called distance problem. So let us see now how to apply this formula for midpoint approximation in a specific exercise. Here we have f of x equal to x squared. We have the interval from 1 to 7. And he said you need to find the approximation by using 3 rectangles or 3 sub-rectangles, okay? 3 rectangles for the area or to estimate the area under the curve. So what should we do? As usual, we will find first delta x. Delta x, as we said, it is b minus a divided by n. A here is the starting of the interval, b is the end of the interval, n is the number of rectangles. So our b is 7, that is 7, minus 1, that's the beginning, divide by 3, as he said. So this is equal to 7 minus 1 is equal to 6, divide by 3, this will be the width of each sub-rectangle, which is equal to 2. Now what I need to do, I need to choose my sample points. So I go to the interval, which is from 1 to 7. I need to divide it into 3 equal sub-intervals. So let us say this is 1. This is another one. I need to find these points. So what should I do? I need to add delta x, delta x, delta x. Delta x is 2 plus 1. That's equal to what? That's equal to 3. Plus 1 again, that's equal to what? 5. So I constructed now the sub-intervals. It remains to choose the sample points. Be careful. If he said the left points, it is direct. If he said the right points, it is direct. But if he said the mid points, you need one more step. That is what? I need to calculate the midpoint between these 2 points. I will call it x1 bar, which is the average of these 2 numbers. 3 plus 1 is 4, divided by 2, that is 2. Then I need to go and evaluate the second point here, which is the midpoint between 3 and 5. Clearly it is equal to 4. 5 plus 3 is 8, divided by 2, that's equal to 2. Next, I have the midpoint between 5 and 7. This is x3 bar, which is equal to 7 plus 5 is 12. Divided by 2, that will be 6. Or you start here and you are adding the delta x. So 2 plus 2 is 4 plus 2, which is equal to 6. How many sample points? 1, 2, 3. How many rectangles? 3 rectangles. So I am doing things correctly. Okay. What is the area now? Approximately equal to. I will call it here M3. Meaning, I am choosing 3 rectangles and midpoint as sample points or midpoint approximation. So the answer will be equal to delta x is 2 times the image at this value. So it is f of 2 plus f of 4 plus f of 6. Now, when you calculate this, what do you get? You get 2 times what? You have the function is x squared. So simply this will be 4 plus 16 plus what? Plus 6 squared, that is 36, which is equal to. You have 4 plus 16 is 20. 20 plus 36, that will be equal to 56. 56 times 2, that will be 112. Okay, so this number is an estimation of the total area under the curve y equal to x squared above the x-axis and bounded between 1 and 7. So we learn how to find the estimation of the area by using right points, left points, midpoints. We know how to calculate the exact area, which is simply done by finding first Rn or Ln and then pushing in to go to what? Infinity. We reach the last point now, which is what is the meaning of the distance problem, okay? And how it relates to the discussion we made. That will be our last point. Now let us see an application for the area problem. Considering the function we have specifically to be the velocity of a particle moving during a period from A to B, the question is, what is the total distance traveled by the particle? If we had the velocity is fixed, then we know that the total distance, the distance is the velocity times the time, okay? But the problem here, we have different velocities at each different time point. So the question, how to find the total distance traveled by the particle? Now, if you figure out again, if you just try to partition this interval, so this length will stand for the time period. Okay, now how to choose the height or the velocity here? We have different type of approximation. You may choose it to be at the beginning, so you are approximating the total distance by using left points approximation, meaning I am taking the velocity of the particle only at the first point to approximate. Or I can take the velocity of the particle to be at the end of each subinterval to approximate. I can also choose it to be the middle point of each subinterval. So I have different type of approximation. If I need to get the exact velocity, or the exact distance traveled by the particle, I need to increase these numbers of the points here to go to what? To again go to infinity. So practically, or in summary, what is the meaning of the total distance? Simply, you can see here, if you multiply, you are adding areas. So the area here under the curve, if this curve represents the velocity of a particle, then this area under the curve will be what? Will give me what? The distance traveled by the particle. Let us take now an experiment and see how to estimate the total distance. Assume you have a speedometer and you are measuring the velocity of a certain particle each 5 seconds. So I measure it at 0, it happened to be 25. At 5, it happened to be 31. 10, you get it 35. 15, you get it 43. 20, you have it 47. And you are trying to estimate the total distance traveled by this in the first 20 seconds. Okay, you see these are different velocities. That's why this point is of interest here. What we will do now, we can estimate the distance traveled by using the velocity at the beginning of each subinterval. We call it left point approximation. Or we may approximate it by choosing what? The right point, the velocity at the right endpoints. We call it right point approximation. So I will say here distance is approximately here equal to what? Approximately equal to, of course, the length of each subinterval is 5. So it is 5 times. Now, if I choose the left point approximation in the first subinterval, I will take the image of the first point, which is 25. So this is 25. Plus, in the second one, which is 5 to 10, I will choose the velocity at the beginning. So that is 31. Plus, for the next one, which is 10 to 15, I choose 35. Plus, at the last one, I choose what? 43. So this type of approximation, I have 1, 2, 3, 4 subintervals. This is what we call left, what? Left points approximation. The endpoints to be left approximation. So I would simply say the left approximation. I'm taking the velocity at the left point. And then you can calculate this to be equal to, of course, you can add these numbers. So I have 3 plus 5, that is 8. Plus 1, that is 9. 9 plus 5, that's 14. So this is 4 and 1. 5, 8. Plus 3, that is 11. 11 plus 2, that is equal to what? That's equal to 13. So I have 1, 3. This is 13. multiplied by 5. Okay, multiplying by 5, this will be equal to 0. 5 by 4 is 20. 0 and 2. 5 by 3 is 15. So that is 17. 7 and 1. 5 by 1. So this is 670. This is given in feet. So the distance here is given in feet. So approximating the distance by using left point as a sample points give us the distance traveled is 670 feet. If you are using the right points, or you can say the distance is approximately equal to 5 times, now taking the right endpoint, so it means the first interval I will take 31. Then I will take the next one is 35. The next one will be 43. The last one will be 47, and that will be what we call right endpoints approximation. Okay? So I am approximating the total distance by taking the velocity at the end of each sub-interval. This is equal to, again, you need to add these numbers. So this is 10 plus 5 is 15 plus 1, 16. So this is 6 and 1. 5 plus 4, which is 9. 9 plus 3 is 12. 12 plus 3 is 15. So this is 1, 5. Then you need to multiply again by 5. That will give you equal to, of course, here we have 0. That is 5 by 6 is 30. So 0 and 3 we have. 5 by 5, 25. And 3, that is 28. So I have 8 and 2. Then I have 5 by 1. So that is 780 feet. You can see now we get two types of approximations. According to the experiment here, we were able to approximate the distance using left point and right point approximation. So in summary, what is the area and distance problem? We have 4 main points. You need to understand what is the meaning of the area problem. You need to understand how to approximate the area by using left point, right point, midpoint. You need to know how to calculate the exact area by taking the limit of Rn as n goes to infinity or the limit of Ln as n goes to infinity. It doesn't make a difference. And you need to understand what is the meaning of the distance problem. That is the distance traveled over a certain period of a function which is the velocity function is the total area under the curve. That is what we call areas and distances.